Hello everyone. So the topic for this discussion is Boolean expressions and how to minimize the Boolean expressions. So the various operator precedence for this Boolean expressions is the operator precedence for evaluating a Boolean expression is in the order of your parenthesis, not operation, and operation, or operation. Examples that we are using in this is xy dash plus your z and your xy plus z the whole dash. The Boolean functions, how it can be given is a Boolean function can be, it can have an Boolean binary variables, it can have binary operators as or and it is having an, it can have an unary operator as not, and it will be having an parenthesis. Examples that we are going to use here is your f1 that is equal to xy z dash, and f2 that is equal to x plus y dash into z, and f3 is equal to x dash y dash into your z plus x dash y z plus xy dash, and your f4 is called as your xy dash plus your x dash z. These are the examples that you will be using for this for the study of your Boolean expressions. So algebraic manipulations, what are the things that should be taken in heart is to minimize a Boolean expression. We need to know the literals are nothing but the operators that we use, operators, and as well as the binary variables that we are using, complemented or in uncomplemented form. And next one is a term and implementation with the gate, and the minimization of the number of literals and the number of terms, a circuit with less component, and so on. So it is a hard problem, so there is no specific rules to follow. It depends on it may get varied depending on the person who solves the problem, and depends on the augmentation of the author or the solver who is going with. And example 2.1 we can take as your x into x dash plus y, which could be given as your by using your postulates, earlier postulates. This could be written as your x dash plus your xy. So this x plus x into x dash is called as your multiplication of a term with its inverse will give you the identity element as 0 plus your xy, which is equal to xy. And the second one is your x plus x dash into y, which is equal to, which could be given as by using your postulates, this could be written as your x plus x dash into your x plus y, which is equal to 1 into x plus y, because an addition operation, arithmetic operation between a number and its inverse will be equal to 1. So 1 into x plus y, which is equal to x plus y. And the next one is your x plus y into your x plus y dash, which could be given as your by using the postulates, which this can be given as or just general multiplication 1, 2, 3 and 4. So you multiply first and third, and you multiply second and third, and if multiply first and fourth and the second and fourth, you will be getting it as x plus xy plus your xy dash plus your yy dash. Now you take, what you can do is, for the in this y and y dash, the value is equal to a multiplication of a variable into its inverse will be equal to 0. So you take x in common, okay, of these three, you can write as 1 plus y plus y dash, which could be given as your x, because the value of your the sum of the number and its inverse is equal to 0 value. So you can write it as so x plus x into 1 plus 0, x into 1 plus 0 is can be given as your the final value is equal to 1, or this can also be written as x plus y into x plus y dash, right, by using and by using the earlier postulate, Huntington's postulate. This could be given as your the x is the common term, so x plus yy dash, yy dash value is equal to 0, so x plus 0 is equal to 0. And the fourth problem is xy plus your x dash z plus your y z. What we can do here is, here you can multiply with this y z term, you multiply with your x plus x dash, the value of your x plus x dash is equal to the value is of your x plus x dash should be equal to your 0. So you can write it as, so xy plus your x dash z plus your y z, the same term, so into y z into your x plus x dash, the sum of number and its inverse, okay, the number sum of number and its inverse. Now what you can do is, we can by this could be solved as this term is to be multiplied with this x, and this term is to be multiplied with this x dash also. So this term will become as 4 terms will come. So xy plus your x dash y z plus your y z x plus your y z x dash, which is equal to, which could be given as, so on these 3 terms, okay, on these terms what we can do is, on solving you will be getting this xy into your 1 plus z, xy into your 1 plus z, and the next one is lateral terms. You can write as, so for between the first and third term, between the first and third term you can take xy in common, so you can write as the remaining will be your 1 plus z. Between this second and fourth term, between the second and fourth term you can take your x dash into z as common, x dash into z can be taken in common, and the remaining will be your 1 plus y, okay. So xy into your 1 plus z, okay. Any variable is added with 1, the value should be equal to 1. So like that, using that principle, here z is a variable, z variable is added with the 1 means the value is equal to 1, and here the variable y is added with 1, the value is equal to 1, okay. So the remaining will be your xy plus your x dash z. And the fifth problem is x plus y into your x dash z into your y plus z, okay. In this, what we can do is, we can this equation is a simpler equation, and it's the same as the equation of your fourth. This is a dual of this thing, okay. This is a dual of this fourth problem. Here also we may get the same answer as of this xy plus your x dash z, okay. So when the question has been dual, the answer will also be the answer that we will be getting is also a dual answer of the answer. So x plus y into your x dash plus z, okay. So 4 is the duality of I, so the result is also the duality of the fourth answer or fifth answer. And the Boolean functions of these 4 functions can be given as your of the 4 functions we have seen here, right? f1, f2, f3 and f4, okay. When you draw the truth table for that, here it could be inferred that the f3 and f4 we are getting the same output, okay, such that the two Boolean expressions f3 and f4 are equal. So if we are getting the two things are equal, if we are getting the same output, what we want to do is we have to realize it with an gates, okay. When we realize the logical function using the gates, here your f2 is equal to your x plus y dash into z. Y dash means you have to invert this y, and whenever you are having a multiplication means you have to, as I have already indicated, we have to use an IC 7408 AND gate, and when you have an addition operation you have to use the IC 7432, that is an OR gate. And this f3 function is also implemented here, but see, on seeing the output with the truth table, the f3 and f4 are giving the same outputs, but whereas the implementations makes to be tougher, this f3 function to be tougher, but whereas your f4 is a simpler implementation, so your f4 is a more economical implementation. And complement of a function, what is a complement is, a variable x is given, the complement of the function x is called as your x dash, the complement of the function x is called as your x dash. So by De Morgan's theorem, where for example if we want to, the complement means interchange, when an input is of 0 is given, 1 is your output, when a 1 is given, 0 will be your output. By De Morgan's theorem, we have been given as a question has been raised as a plus b plus c the whole bar, which is equal to, here instead of this b plus c variable you take a common variable as your x, a plus x bar, okay. Let b plus c be your x. Now what you can do is, this is called as your a plus x bar can be given as your a bar into your x bar. This is by using the theorem number 5a, that's your De Morgan's theorem. Now instead of this x, you replace it by your b plus c the whole bar, okay. So here again by using De Morgan's theorem, b plus c the whole bar is called as your b bar into your c bar. Now this could be replenished as a bar, b bar and c bar. This is by the theorem number 4, which is called as your associative theorem, okay. And there are few other understandings and generalizations as of your and an or operation is about. And this is an example number 2.1 and 2.3 which has been solved, okay. So see here, this is a direct how duality is helpful, that could be easily studied by using this example 2.2 and example number 2.3. So now see, this f1 dash, okay, f1 is the function that we already know, okay, f1 dash, okay. So what we are going to do is your f1 dash is equal to x dash y z dash plus your x dash y dash z the whole bar. So that is your f1 is a function called as your x dash y z dash plus your x dash y dash z. If you take a complement, you will be getting you have to put a dash here. Okay, so this is looking like a plus b be the whole bar. Okay, a plus b the whole bar means a bar into your b bar. Now the negation has been split amongst two. Now what we can do is you can use the now again you have to use your theorem. Okay, which theorem? That is your De Morgan's theorem. This is called as ABC the whole bar. ABC the whole bar is a bar plus b bar plus c bar. Here instead of the a you have got it as x bar. Okay, so x bar the whole bar is called as your x, and y is there. Okay, plus y bar. Okay, plus z bar the whole bar is equal to your z, and the remaining here a b c the whole bar can be given as your a plus b, a b c the whole bar can be written as your a bar plus b bar plus c bar. So a bar means x bar the whole bar is called as your x, and y bar the whole bar is called as your y, and z bar. Okay, x plus y plus z bar. And f2 bar means, f2 dash means, now the function is called as your x into this function can be given as your x into your y bar, okay, into your z bar plus your yz. Okay, now here what we can do is you have to take the entire complement. If you take the complement, this is called as your a, and this term completely called as your b. Okay, a is your x, and instead of b is complete y bar z bar plus your yz. So ab the whole bar means you can write it as a bar plus your b bar, a bar plus your b bar. Now what we can do is this a bar plus b bar is there, right? So now we can write it as this b plus this is two terms are there. So here we can write as b plus c the whole bar means b bar into your c bar, b bar into your c bar. Now again you use De Morgan's theorem. This is called as your y bar z bar the whole bar means this could be given as so for example ab the whole bar can be given as your a bar plus your b bar. So instead of a you are having it as y bar, and instead of b you are having it as z bar. This could be written as your x bar plus your y plus z, okay, into your y dash, okay, y dash plus your z dash. That's the same. So this number, example number 2.2, a simpler procedure, okay, to do the same problems is, okay, the complement how it can be founded is you take the duality of the functions f1 and as well as your f2. Okay, you take the duality in before finding this f dash, f1 dash and f2 dash. You take up the function f1 is x dash y z dash plus your x dash y dash z. So you take the dual function of that. When you take the dual, what you want to do is you have to change the positive sign into multiplication signs, and as well as that is your additions into multiplication and the multiplications into additions. You take it as dual, okay, and as well as ones to zeros and zeros to ones. Okay, so after taking the dual, now you take the complement. Okay, if we take the complement means then it's called as your complement each literal means when you take the complement of each literal, so x y bar into your plus z and your x plus y plus your z bar. This is called as your y1 dash. Okay, like the same, if this is called as your sum of the products, this is called as your sum of the products. So by taking a dual means it will become as your product of the sums. Okay, product of the sums. So these are all the sums, product of the sums. Okay, now after taking this product of the sums, you have to complement the literal alone. This is an easiest procedure as of the complementation progress is about. Okay, and the next one is called as your canonical and standard forms. Okay, canonical and standard forms are, there are two different types of forms as I've already indicated. This is called as the sum of the products. Okay, and this form is called as your product of the sums. Okay, product of the sums. So the standard forms and canonical forms means here you will be having just two things. One is your sum of the products and next one is called as the product of the sums. Okay, there are two terms. One is called as your min terms and next one is called as your max terms. Min terms means, okay, min terms means what you can do is it's a standard product procedure, and this max terms means that's called as a standard sum procedure. So here what you will be doing is, for example, two binary variables x and y is there means xy dash x dash y and x dash y dash. This is called as your standard product procedure, and here opposite to that you will be getting this x plus y dash x dash y plus y, like that. Okay, there are two pair of that may, and also one more thing, in min terms you will be multiplying, you will be having dot operation, and whereas in your max terms you will be having the OR operations, addition operations. Okay, and the next one is, so min terms and max terms. As of the min terms and max terms is about, now see here, for example, x, y and z, take the inputs from your 0 0 0 0 to 111. Now this could be designated as x, y and z, so this can be written as your x dash, y dash and z dash. This is called as a min term expression. Okay, the x dash, y dash and z, and x dash, y, z dash, and x dash, y, z, and your x, y dash, z dash, like that you will be getting. This is the terms, and the number and the min terms will be mentioned as small m. Okay, small m naught, small m1 and up to small m7. So this is called as your products. Okay, that is you will be using your AND gates. But whereas the sum terms is about, means what you want to do is, instead of this, okay, you have to write as, you have to invert, and you can write it as x plus y plus z. Okay, x plus y plus z, that is a dual of that. Okay, so your x plus y plus z bar, and your x plus y bar plus z, and your x plus y bar z bar. Okay, like the same, this is an invert of this. Invert of this means the complements will be, the terms which are will be having complements, the literals which have complements may not have complements here, and also here it is a product term, it should be a sum term. The designations are capital M0 to capital M7. Okay, each max term is the complement of the corresponding min term. This we have to keep in our mind. And min terms and max terms is about, now let me take a small example. So see here, the function f1. Okay, function f1 is, so your x dash y dash into your z, x dash y dash into your z means 0 0 1, and your 1 0 0. Okay, and your 1 1 1. Okay, that is your m1, m4 and m7. Okay, on that cases alone you put 1 and 1 1. Okay, and for your f2 function is given as your 0 1 1 and your 101, and this called as your 110 and your 111. For these values you put the values of 111. Okay, so this is your function f1 and as well as your function f2. As of the min terms and max terms is about, as of the min terms and max terms is about, so your m1, m4 and m7, and the next one is called as your m3, m5, m6 and m7 are the min terms and max terms for the given table number 2.4 illustrates the same. So the complement of a Boolean function. Okay, the min terms, the complement of a Boolean function means here f1 is written for the values for which it is giving the value of 1. Okay, and f2 is written for which it is giving the value of your 1. Okay, f1 bar means, okay, f1 bar means it should be the values. Okay, it should be the values for which it is giving zeros. That means this x bar y bar z bar, and your x bar y z bar, and your x bar y z, and next one is called as your x bar x y bar and as well as your z, and the final is called as your x y and z bar. Like the same thing you would have got here, and this f1 is called as your f1 bar the whole bar. Okay, so now what you want to do is, this is called as your sum of the products. Okay, this is called as your sum of the products that can be converted into a product of the sums, the product of the sums. F1 bar has been founded. F1 bar the whole bar is called as your F1. Now what do you want to do? As per the sum of the products and product of the sums, we have to change the complement of each literals, and instead of the product terms you have to include the addition terms. So now this is called as your this is expressed in min terms, and this is expressed in max terms. Okay, like the same you can do it for the f2 function also. Okay, so what is the thing you have to do is, you have to take to find the complement of the Boolean function. When you want to find, you can this is a sum of the product form, and this is called as a product of the sum form. Sum of the product and product of the sum, how it varies is just the addition operators should be changed as dot operators, and the dot operators should be changed as addition operators, and each literal's complement should be changed to uncomplemented values. And as of this, The next thing that we have to see is called as your example. This is another one example. I'll be posting a few more videos for doing the Boolean expression solving. Okay, I will solve and show you. This is another example which is given as express f that is equal to a plus bc bar, okay, as a sum of min terms. Okay, so you can write it as the given, it can be written as your f that is equal to a plus b bar into your b bar into your c. So a plus b bar into your c, which could be given as your, which is equal to a into, okay, so with this I am concluding this. The remaining problems we may see in the next talk.